All right, so today we are going to very quickly review the basics of stoichiometry. And so this coincides with the section 4.5 in the AP curriculum. Essentially, stoichiometry, if you'll recall, is just using a balanced equation to determine the amounts of products produced or to figure out the amount of reactant that you need. It's going to involve grams. You may be given moles, maybe volume of an aqueous solution. So if you're given the molarity, you might be asked for volume in milliliters or liters, or you may be given the molarity and the volume and asked to convert that to grams or moles or something else. And then, of course, we've also talked about gases already, and gases can be involved as well using the ideal gas law. A couple main terms. Hopefully you remember, but if you don't, we've got limiting reactant. This is, of course, the reactant that runs out, and this is what determines how much product you can make. The excess reactant, obviously, I didn't even define there because it's pretty simple. It's the one that's not limiting. It's the one that you have some leftover of. Actual yield, what did you actually produce in the lab? Theoretical yield, using the math, using the stoichiometry, what should you have made? And of course, percent yield is a term that simply means actual over theoretical divided by 100. So we want to get as close to 100 as possible. All right, let's take a look at an example here. So here we have a balanced equation. We've got some coefficients. It says in the reaction represented above, the number of chlorate ions that are produced is equal to which of the following? So just kind of go through one at a time. We've got our chlorate here, which is a coefficient of 1. So is chlorate equal to 1/2 of Cl2? And of course, you can see it's equal to 1/3. So there's 3 Cl2s consumed for every 1 chlorate. So that one's not correct. 6 times the number of hydroxide ions consumed. No, that would not even be close. 1/5 the number of chloride ions that are produced, and that one looks correct because we're producing 5 chlorides for every 1 chlorate, so it looks like we're looking at C. All right, one more here. We've got another calculation here, another equation here, pardon me. This one does involve a calculation. We've got carbon monoxide and hydrogen making methanol gas. A 56 kilogram sample of carbon monoxide and a 6 kilogram sample of hydrogen are combined in a closed vessel where they react according to the equation above. So after the reaction has proceeded to completion, how many moles of methanol have been produced? So one thing you can do to simplify this and make it a little bit faster is, if you'll notice, they're giving us kilograms of each reactant. And so we can probably just look at those as grams, especially because if we look at all of our answers, we've got everything times 10 to the third power moles. So if we just sort of artificially change 56 kilograms into 56 grams and do the same thing with the 6 kilograms, just consider it grams, and then just ignore all the 10 to the third powers, those two sort of opposite changes that we're making to the problem cancel out, and it makes everything a lot quicker. So you can do this a couple different ways. One way to do it, when you're given amounts of both reactants, remember you don't know which one is limiting just by looking at the masses. We have to do a little bit of calculation. Sometimes you might be able to quickly eyeball it and see which one is limiting, but usually because a mole of carbon monoxide weighs a lot more than a mole or even 2 moles of hydrogen, we can't just look at this and necessarily know which one is going to be our limiting. So we do have to do some stoichiometry. And there's a couple different ways to do that. You could convert both numbers into moles and then analyze it and see, okay, is it 1 to 2 or is it something else? One way to do it, the way that I always have done it, is if you just simply take one of the two reactants. In this case, I'm going to say 56 grams of carbon monoxide, although I could have started with my 6 grams of hydrogen. But I'm going to choose to start with my 56 grams of carbon monoxide. And I'm going to go ahead and convert that to see how many grams of hydrogen would be needed to react with that much carbon monoxide. And so this 28 grams per mole just comes from the periodic table. The 2 moles of H2 for every 1 mole of carbon monoxide comes from the balanced equation, right? That's just the coefficients. And then again, periodic table to go from moles to grams, this time of hydrogen. And so what I determined is that I need 8 grams of hydrogen to fully react with 56 grams of carbon monoxide. And the next step is to evaluate, okay, I need 8 grams of hydrogen, but I only have 6. Again, we're ignoring the whole kilo thing because we're just treating everything as grams, and we're going to come up with a number that is just the coefficient rather than this times 10 to the third power. So if I need 8 grams and I only have 6, then what does that mean about hydrogen? So hopefully you're saying I don't have enough hydrogen. I only have 6, I need 8. And so once you realize that hydrogen is the limiting reactant, we're going to use it to predict not grams, but moles of the methanol. And when I do that, I should come up with about 1.5 moles of methanol. So again, we just went to the periodic table to go from grams of hydrogen to moles of hydrogen, and then the balanced equation to go from that to moles of methanol, and I get 1.5. Now technically it's 1.5 times 10 to the third, but I am, I'm using grams here to go to moles. So since 6 grams is 1,000 times smaller than 6 kilograms, that's why my answer is 1,000 times smaller than the choice A here. So 1.5 times 10 to the third moles of methanol would be expected. And there we go. That's our intro to stoichiometry. We'll be doing a few more problems as we go here to get refreshed.